So just write H3O plus because this is your acid catalyst and your nucleophile in one. When this H3O plus gets attacked by the alkene, it's going to get deprotonated and it turns into H2O. And then this H2O is going to act as your nucleophile. So just don't get tripped up if you just see an H3O plus. But the mechanism for this is this: the alkene just attacks the acid catalyst, the H plus, and then you have your nucleophile, which is, so after it attacks the acid, it's going to open up, and then the hydrogen gets placed on the least substituted side in Markovnikov fashion. And then the most substituted side is going to open up and become that carbocation. So with this reaction, you have a carbocation intermediate, which means you have a full step where you just have this cation. This allows rearrangements. So if you have, let's say, a quaternary carbon next to this, let's say our carbocation was here. We can do a methyl shift from one of these quaternary carbons onto this, and we get a more stable carbocation, a tertiary one, right? So just look out for that. That's very important with this reaction. And there's actually one question in the extra credit thing he went over today that I didn't agree with, and I'll pull that up after. So yeah, watch out for rearrangements, and then the nucleophile of the water is going to attack the carbocation, and then you just get your alcohol product. There's no stereochemistry, so this is going to be just a racemic mixture. It can add any direction.
So you're saying if we see the isopropyl or the propyl and we have the carbocation to make it the most stable, that's the first thing we would do, rearrange it. That's what you like.
Yeah, if you have something that would make it a more stable, more substituted carbocation, then you would rearrange it. Yeah.
Do you know if we're gonna see much of like ring expansion and stuff?
Maybe like one question. Or none. I don't remember like him using it that much.
Okay.
What was the green?
So the green was just demonstrating like a rearrangement. So what happened was the methyl shift went here to make a more stable tertiary cation. Yeah. Okay.
And then
Oh, sorry.
one more thing, sorry. So what other reagents could be there possibly that would make it acid catalyzed hydration? So like as soon as you see it, you're like, okay, wait, this is what I'm gonna do.
You could have H2SO4 and H2 on top. Usually it's like one of these two, the H plus and the H2O combo, or the H2SO4 and H2O thing. Or you can have like HBr and OH minus, any acid and any nucleophile together. But next we have oxymercuration, demercuration. So for this one, it's going to be Markovnikov, and there are no rearrangements. So there is a transition state, which is where we see like the Markovnikov carbocation and hydrogen arrangement, but it's not actually an intermediate step. So we don't get a full molecule that has a carbocation. We just get this kind of weird partial bond thing. But in this reaction, what happens? The alkene attacks the mercury, and the mercury like attacks it back, which is why you get that triangle. And yeah, once you get this triangle, you have the delta positive on the more substituted side. So you get this solid bond with the mercury, like this one is not dotted, which means it's a real bond and not a partial bond. And then this side is going to be a partial bond, so it's not a full thing, which is why this carbon right here is delta positive. Because the more substituted carbon, the secondary one is delta positive and not this primary one, this is going to be Markovnikov. And because we have a delta positive, you know, your nucleophiles like to attack the electrophiles, which is the positively charged one. So the nucleophile, water in this case, is going to come in and attack the carbon that has that partial bond delta positive. And then you can also have an alkoxymercuration, which I don't know if he's going to add that. But an alkoxymercuration is just where you have an alcohol instead of a water as your nucleophile, and then you would get an ether. But just don't worry about it, just note. And then after that, you get your alcohol attached to the alkene, your alcohol attached to the more substituted side, and the mercury thing attached to the less substituted side. Then you have to do your last step, your demercuration, which is done by NaBH4. The NaBH4, all it does is it replaces this mercury with this hydrogen. There's no stereo selectivity, so it's not going to be syn or anti, it can be whatever. It'll be a racemic mixture, and then there's no rearrangements.
We can't see the.
Oh, sorry. Oh,
Yeah, the end.
How does it get rid of the,
I don't know the mechanism. No one ever teaches it, but it just does.
because that's, yeah, no one ever taught me the mechanism.
Yeah, it's probably something like complex, but I like Googled it once and I didn't want to bother.
It's just hard because, they use NaBH4 for other stuff too, so I'm trying to picture what it looks like, but.
Well, it's used for reducing, right? It'll just add a hydrogen. I guess that's what you need to associate NaBH4 with.
Yeah.
But the third one is hydroboration oxidation. This is the net anti-Markovnikov, but technically it is Markovnikov because of this intermediate state. But anyways, we're going to start with an alkene and the following reagents. We're going to have a BH3 CHF on top as your step one, your hydroboration. Then on the bottom, we have H2O2 and NaOH as the oxidation, so step two. So in step one, with the BH3 and THF, you are going to get this transition state. So what happens is the boron and the hydrogen and the alkene kind of attack everyone like all at once. So you get a giant partial bond, you get a giant square of partial bonds. And the thing that Roche really loves is you have this delta positive on the more substituted side. So when you have this transition state, the least substituted side is going to get the delta positive, and the more substituted one gets the delta negative. Is this the delta negative? And then the more substituted one gets the delta positive. This makes it technically Markovnikov, but the actual product, since the hydrogen ends up on this side, it's going to be anti. So after you get this, you just get the BH2 complex on the least substituted side, and you get the hydrogen on the more substituted side. After you get that, you do step two, the oxidation with H2O2 and NaOH, and you get your product. All this does is it replaces the BH2 with an alcohol. Oh, and it's a syn addition, so the alcohol and the hydrogens are going to be facing the same plane. So they're both going to be dashed or they're both going to be wedged, which is why we always write plus in enantiomer.
What's the addition of the oxymercuration, demercuration?
The addition?
Is it syn or anti?
Oh, it's neither. It can be whatever.
Oh, yeah.
Yeah, the hydroboration oxidation is the only one that does like a syn addition. The rest like don't care.
Is there any other reagents that we would see?
Yeah. So there isn't a reagent, but there's like a modification of the reagent, which we did a problem about it up here. Yeah. So if you look at this one, instead of a BH3, we have a BD3. Then the D is deuterium, which is the hydrogen isotope. So because you have the D3, it's really important to know the square. Like you should really know what the square looks like so you can assign the D and the H to the right place. So yeah, you have to know which side the boron goes on and which side the single hydrogen is going to go. And then once you just draw the square, you can break it open and then you'll get your answer like that. And then another thing people sometimes get confused about is that for the OH, they'll put like OD. I did that quite a few times, but since that step is completely separate from the hydroboration, it's its own thing with H2O2 and NaOH, you're not going to do anything to the alcohol. It's just going to stay normal alcohol.
And so that's why the number one was right and number 4 was wrong, because the D is in the wrong spot, right? Like when it attacked because of that whole process.
Yeah.
Okay.
So in number 4, the alcohol is on the more substituted one, which would be the wrong regioselectivity. Okay. So after we get our alcohol, we can turn it into a halogen. So the reactions you want you to know for this are this first one, which I don't know what it's called. Acid catalyzed halogenation, who knows? But for this one, you're going to take a secondary or tertiary alcohol, so you can do an SN1 reaction. And this one, you just take the alcohol, and it's going to be your nucleophile and base, kind of, and it's going to attack a strong acid. So by strong acid, we can only have HBr or HI. And does anyone remember why those are strong acids and not the other halogens? Yeah. So the conjugate base of HBr and HI are going to be more stable because of atomic size. If you have a HCl or HF, those are going to be less stable conjugate bases because they're much smaller atoms. So you can only use this, HI or HBr. So the alcohol is going to attack the H of the HBr, the Br leaves, and then you get this water onto the alkane, which turns into a good leaving group. And this is tertiary and secondary, remember, so it's going to be an SN1 reaction. It's too sterically hindered for the bromine to come back and do a backside attack. There's nowhere to actually do the backside attack. So the leaving group, this water, is just going to pop off and leave, and then we get a carbocation. And then the bromine comes in as a nucleophile, it attacks the carbocation, and then you okay, so that was one way to activate the alcohol, was to turn it into a water. We can also use like a Lewis acid and a bulkier like addition as a leaving group to make the alcohol into a good leaving group. So in this case, used ZnCl2, which is a Lewis acid, which means it's an electron acceptor, so an electrophile. In this case, the alcohol is going to go ahead and act as a nucleophile and attack the electrophile ZnCl2. And then you get this giant complex, which is a really good leaving group. Once you get this, I guess the HCl or some Cl ion is going to come in and then attack in SN2 fashion. It's going to come in and attack this carbon. Then this whole thing is just going to leave. And it's SN2, so you get an inversion. I didn't draw it here. I should just write it. And then you get another alkyl halide. I wouldn't like worry about the mechanism specifically. You should just know like the general idea. So for this one, the general idea would be the alcohol attacks the ZnCl2, becomes a good leaving group, and then you get the alkyl halide.
Can there ever be a scenario where it is like stereoselective?
Where it's what?
Stereoselective?
Like syn or anti? Oh,
Like the Cl when it attacks?
I mean, beyond it just being like a backside attack and inversion, I don't think so. Yeah. Oh yeah, and this is called activation. Activation means making the water or the alcohol a good leaving group. So then you have these reagents. You have PBr3 and Sokol2. And then this is going to happen over purity or purity. This is milder. I don't know what milder means. I know Roche said it, and like I just memorized it. I don't know what mildest means.
That's what I have too.
Yes. So this is a milder method, not the mildest. And what happens in this, you attack the Sokol. So you're going to attack the S. I'm not going to say SOCl2 every time.
No, I like Sokol.
Thank you.
It sounds fun.
So you attack the S because it's electrophilic and this is nucleophilic. You attack the S. There's like this weird mechanism where instead of the Cl just leaving as a leaving group, you have to like rearrange the electrons of the oxygen. So what happens is one of the bonds goes up, makes it like a negative oxygen, and then this other bond is going to come down and reform the double bond. And the reformation of that double bond kicks off the Cl. But I think that's a pain to memorize. So I just do like the oxygen attacks the S and the Cl leaves. But just be aware that's not the official mechanism.
After it says it's like a circle happening like, today.
Yeah, like it's
Yeah.
gonna be a circle around.
Like in the notes, he wrote it like that, but really it's just like that was the first step. And then he wrote another one showing you where it's doing the circle. But in the notes, it might be a little confusing because he literally draws that and then draws that again. But it's really two different steps, but it's just.
So weird that it's- maybe I would some stuff, but-
Yeah, but he like wanted to write.
Oh,
But like yeah, he's.
We're not
completely
thinking
wrong.
about kind of like the period when it touches the sulfur.
No.
Do we always have to like note that?
Six steps.
Sorry, you guys know what?
Do we always have to note the intermediate when the purity goes into the sulfur and replaces the?
Doing the intermediate, like the partial bond, or like this kind of intermediate? Well, yeah, because it has a name. If it has a name, it's generally important. And just know that this is the pyridinium intermediate. The pyridinium group is the good leaving group.
And that happens for both like slates and tonsils, right?
That's a little different, but like, basically. The whole point of everything is to attach something to the alcohol and make it a good leaving group, and that's what happens with the methylates and tosylates. Okay, so you get that whole like electron transfer thing, and then the Cl leaves. When you're left with one Cl, or when the alcohol is fully attached to the sockle, then the pyridine, the base, is going to come in and abstract this hydrogen. So when the alcohol is attacking the sockle, it doesn't get rid of this hydrogen. The only thing that leaves is the chlorine. So we need to bring something else to come in and take this hydrogen away so we can neutralize the oxygen. So that's what the pyridine does. And this reaction, the pyridine has two roles. The first role is to act as a base. So in this step, that's what it does. And then the next step, it's going to act as a nucleophile. So after we've extracted this proton, we get a neutral charge from the oxygen. Then the pyridine comes back and acts as a nucleophile, and it also attacks the sulfur. Once it attaches itself to the sulfur, you get this pyridinium thing, which is a very, very good leaving group. So we could have just stopped here and like made it leave, but that wasn't good enough apparently. So we have to make this. After you get this, you have a good leaving group. So the chlorine ions from what we kicked off can come back and do a backside attack. Then you get an SN2 with inversion, and then you get these products. For this, this is a pyridinium thing, but it's split apart. So what happens is like, this is the more stable way for those two molecules to exist. So instead of staying bonded as this, it's going to spontaneously just like split apart and turn into these two. But you don't have to worry about that. That's basically how those halogenations are going to go. And then we have the mildest way, with the I still don't know the full name of these. The methyl sulfonyl chlorides. What?
If I went to a wing place and they said, we have mild, milder, and mildest, like, I don't.
You're thinking mechanisms now.
You're forever be cursed with that.
The thing is, he didn't even tell you like what it means. You're just like, this
He
is the
just
mildest.
It happens, but it's like mine.
Like on the road spectrum.
Every time he added it, like mildest, I was just like, it's just harder. It's just longer and harder, and that's it. I don't know.
Yeah, I guess.
Is it just like a bigger, like, is it like a?
Oh, yeah, right.
I don't know. I have no idea. Yeah.
It's less aggressive.
Maybe just make more people cry.
The milder it is, the more it makes you cry.
Does like the mild reactions have like more steps to them?
Yeah.
No, I didn't. No, because the one we just did was milder and it had like
every
5
time you
steps.
add, it's more steps. So like milder was like a lot of steps.
This one has, no, the mildest has less steps than the milder, so I don't know.
But this one was easy the way you explained it, because you were kind of like, this one,
Wait, the
copy
softball
and
one?
paste. No, the next one.
Oh, yeah,
Like,
this
you were
one?
like copy
Yeah.
and paste, so it kind of was like
Oh, I
easier.
see, yeah.
But he
Yeah.
makes like a whole thing.
So for these sulfonyl chloride things, you basically have this as a backbone for the molecule, the leaving group, whatever you call it. You're gonna have the SO2Cl, not, well, it's technically a sockle, but the real sockle is SOCl2. This like fake alcohol is SO2Cl. So if you see that, don't get confused.
It's simple.
But, oh, also one thing, he might like write out the formula like this. So for methyl, he would do like CH3SO2Cl. And then you'd be like, oh my God, what is that? But just like break it up and you see the SO2Cl and then the CH3, and you know it's gonna be the methyl, the MsCl. Yeah, so that's how we name these things. That's the methyl thing, the MS. Then we have the tosyl, the TSCl, and then this group right here, that's like lollipop is gonna be the tosyl. And then we have the trifluoromethyl, which is this thing. You have 3 fluoros on a methyl, surprise. And this one is going to be the most reactive. So how do you do a mechanism with this? All you have to know for these is that the alcohol glues itself to the SO2Cl, and then the pyridine is going to come and neutralize it. So that's exactly what I drew here. You have the alcohol, it's going to go and attack the sulfur. The chlorine is going to leave, and then you have to deprotonate it. I didn't draw it here, but just know the pyridine comes up and deprotonates the alcohol. Now you have this whole thing, which is a trifluoride, I think, and it's a really good leaving group. So after you get, I didn't write this, but in this step, the stereochemistry is retained. So when you're gluing this thing onto the alcohol, you don't do any inversions. It stays like wedged or dashed. In this case, it stays wedged.
In the chair, that way you drew it as a chair, so I kind of remind yourself.
Well, I copied this from his notes, so I guess that's why he drew it as a chair to show the stereochemistry. But I also drew it down here. So in the first step, when you're adding the weird sulfur sulfonate protecting groups, the stereochemistry stays the same. But when you do the second step, when you're actually replacing the leaving group with the halogen, then it inverts. So you see this pointing up here, it's wedged, but then we get the LiCl. And I don't think you need to know why we use this and like DIMSO, but just in case, these bottom things are polar and aprotic, and it kind of like organizes itself around the Li and Cl ions. So it's going to encourage that salt to break up and turn into nucleophiles. Where was it? Yeah, so the chlorine. So this is going to break up because of these things on the bottom, and you're going to get Cl minus. The Cl minus then does an SN2 reaction, a backside attack where this protecting group is, so the TF in this case. After this SN2 mechanism, you get an inversion of stereochemistry, so it went from wedged to dashed. So overall, the stereochemistry inverted, but in this step, it stayed the same. And the second step was really where the inversion happened. So if you want to change the stereochemistry overall, you know you're going to want to use this kind of protecting group, followed by another step that inverts it,
So it's just substitution with 6 extra steps.
basically. Oh, there's more. Okay, so we have Williamson ethers. Oh, can I move on? Is that good? I mean, you're posting it, yeah. I am posting this, yeah.
Which one is the protecting group again?
So all of these are protecting groups.
Okay.
And then you just know that the actual, like when it's protecting the alcohol, this Cl is just going to be replaced by the alcohol. It's like in its actual final form, instead of the Cl, you're going to have the alcohol attached there.
Okay.
Or should I keep this up?
Do all 3 of them give that version sense order?
Well, all 3 of these are non-inversions. The whole point is like, it keeps the stereochemistry of the alcohol the same, so the leaving group is the same as the original alcohol. And then in the second step, if you want to replace it, then it inverts. So like overall, from alcohol to halogen, it inverts. But if you're using these, like that step alone where you use these protecting groups, it won't invert. Was there anything else, or do you just go straight into the ether synthesis? Really?
He like talked about one question.
Today was like the first day part. The way I know it's just a sun that you see here. So you got no crowd.
Okay,
It's showing us.
This was like the last thing that he went over in class, the other last class. It's like literally the last thing that he went over. So he did go over it, but like very briefly. I think he did one with K.
Yeah.
OT or something. Yeah.
well, do you guys want to do it or do something else?
Yeah. This is
Okay.
probably the one. And a-
So in a Williamson ether synthesis, you start with an alcohol, an alkyl halide, and a base, a super strong base. And then you add those together and then you get an ether. But what actually happens is you start with the alcohol and you have to turn it into a good nucleophile. You do that by deprotonating it. So usually we just use NaOH, but Roche has like a vendetta against NaOH, so he has us use these super strong bases. So we can use NaH minus, we can use this BULI, tert butyl lithium, and then we have BULI, we also have this NaHMDS thing, which just looks like a crab, I guess. But, and then the only case where he used KOH was when he had a phenyl, so phenyl, I guess, is going to be more acidic because it's stabilized. Because that's more acidic and ready to dissociate, we can use a weaker acid like KOH to get rid of it. Another thing you should note is that all of these super strong bases, they like deprotonate, they deprotonate the alcohol irreversibly. So I think if you have something like KOH or NaOH, you can like do an equilibrium kind of thing with the alcohol and the base. But for these, like once the hydrogen is abstracted, it's just gone. So you have like a permanent alkoxide to deal with. And we deal with that by giving it an alkyl halide. So once you give a good nucleophile like an alkoxide and alkyl halide, the alkoxide, the oxygen is going to go ahead and do an SN2 reaction. So here it attacks this carbon from the back, and then the bromine leaves SN2 reaction, and then we get an ether. That's literally it. And then we can also do an intramolecular Williamson ether synthesis, which is where you have these vicinal things. You have a vicinal alkyl halide and also an alcohol. The proper name for this is a halohydrin. So if you have a leaving group and this nucleophile 1 carbon away from each other, you can go ahead and, well, not even 1 carbon away. As long as they're on the same molecule, the intermolecular Williamson ether synthesis would happen. So even if you had something like this, like you would do the same thing and then also get an ether. So in this case, we're doing it on vicinal things, but you could also do it anywhere in a molecule. But what happens here is the same as what we just covered. It just happens closer to each other. So the super strong base is going to come in, it's going to deprotonate the alcohol. So you get your alkoxide. And the alkoxide goes in and it attacks the back of this alkyl halide. So then the chlorine leaves SN2 reaction, and then you get something called an epoxide, which is a 3-membered cyclic ether. And this, yeah,
If the chlorine was cis, the alcohol, would it not be able to work?
I don't think so, because you wouldn't be able to do a backside attack. Because right now it's arranged like this where the alcohol is up and the seal is down, and you have to get that 180 degrees to get the SN2 inversion. And since it's in a ring, I think the ring would be like the thing that locks it into this conformation. So if they were both wedged on a ring, then I think you couldn't do it. But if they were both like, then I think you can rotate around the single bond and get something wedged. But I don't know, I'm not 100%.
How would you know where it would like make that second bond? Because like to me, I would think of like ring strain and try to avoid that, but apparently that's not something that.
Circumstances, man.
It's just not enough of a thing to make the reaction not happen. So, like, yeah, I don't know. The thing that basically just happens is that these extra electrons from the oxygen, while it's doing the backside attack, it's also forming a new bond. So the attack would be the formation of this second bond to that carbon. That makes sense. Like I just think of the arrow replacing. It's with this bond.
See that? Ortho to that position.
I think if you're making an epoxide, then it has to be.
On today, Irving, this is Tammy's house, rookie.
Let's see what.
I think it's.
Okay,
We're
so
talking about wings flavors, checked out.
what were we talking about? So yeah, so the bond. Yeah, so this arrow literally just turns. Yeah, this arrow just turns into a bond, which is this thing, and you get your epoxide.
That's great.
Can you explain why we would use NaH over KOH and like?
NaH is
Could
just,
you use KOH in the same instance?
in this case,
Yes.
I don't think so because this proton is not that acidic. So you need something stronger to like rip it away. I think he used KOH with the phenol because the phenol hydrogen is kind of acidic, so you don't need something as strong to take it away. But in this case, you have to use one of these.
So when we see a phenol, then we know we're gonna use KOH.
No absolutes. You could use KOH.
You can use KOH.
You may,
You may.
you may use.
There's always curveballs.
But yeah, great. That's how we get epoxides, and that's also how we get like normal cyclic ethers like this. Oh, does anyone want to propose a mechanism for making this?
OH.
What are we making?
Choose OH.
To get this thing?
Like that, oh, is that the product or?
Yeah, this is a product. Oh, so
I had a question like that on my homework.
Yeah, like a retrosynthesis.
Yeah,
Well, does anyone want to try it?
but it wasn't 6.
From what though?
It was like a OH and alcohols in ether, like carbons and NPR.
Oh, I guess that would be breaking ethers,
like-
which he has not talked about. Yeah.
Do you start with the pentanol? So that would be
Would you start with what?
the pentanol.
Wait, tell me. Yeah.
Do we have like a halogen somewhere? maybe?
Where?
You have too many carbons.
Oh, yeah.
So where's the halogen gonna go?
On 5.
On the fifth carbon. Or-
Yeah. Now what?
We need something to kick off that feeling.
Yeah, so how do we turn the oxygen into a good nucleophile that can kick off the BR?
Yeah, it's a protein.
NaH.
Yes, we can use NaH. And I use NaH because it's the easiest to write.
Can you use OH negative?
What other reagents can you use to deprotonate it to make
That's what
oxygen
my-
into a good?
The crab.
All of these. You can use the crab.
Break up the crab.
I just hate the crab because the letters are ugly, this actual structure is ugly, and these are just like not memorable. No one's gonna think like, oh yeah, BULI, of course.
But I'm saying, like, is there anything else that's like, I guess, a mild basic or a mild
Like
base
to replace KOH.
that could replace NaH instead? You know,
The NaH is part of the super strong ones.
So technically you could use these.
Yeah, so NaH and all of these are in the same category. They're all super bases.
Yeah,
I just use NaH because it's the easiest
it's
to
the
write.
simplest one. I
Yeah.
mean, if you want to go that route, you can be the mildest.
Yeah, if you want to use tert butyl lithium, go ahead. It's the same thing. Wait, where did it go?
Yeah.
Oh, okay. So yeah, then you would use a super strong base to get rid of this proton, and then you would just attack, and you get a cyclic ether. Cool.
So that just makes it a ring.
Yeah.
Yep. It's like a-
So like hard to like visually see, but like I guess.
Basically, like the VR leaves and then the extra electrons from this oxygen turn into this bond.
Okay.
So it's, the negative charge on here is gonna turn into a bond on this, which connects it to the other end of the chain. So it's like, think of a piece of yarn, I guess. You're just
And
taking
then
one
just,
end
like-
and like swinging it over to meet the other.
Yeah.
Yeah.
So the VR and NA, they both leave the NA.
Well, the NA was like never attached to anything. It was just like chilling with the hydrogen.
Oh,
Yeah.
And so if the VR was in like position 4, let's say, so then that's how we know it probably have like an echo sticking out or something.
Yes, exactly.
I'm not-
Then if you have the, yeah, if you have like the halogen somewhere else, then whatever's like on the other side of the halogen like this, that just gets turned into a
Oh,
substituent.
yeah, okay.
Do you want to do more epoxidation?
Well, that one this one we didn't even touch. This one, like, the only reason I knew it's the only one that looked different and it was at the end of like the chapter.
Yeah, so this one is like interesting.
Yeah.
All you have to know is that if you see this like MCPDA or anything with 3 oxygens in it, so like CO3H, like it's gonna be a peroxy acid. When you have a peroxy acid and an alkene, all you're doing is copying and pasting an epoxide onto the alkene. So we can, yeah, let's just look at the mechanism for this. What happens is that this bond between the 2 oxygens is super weak and gross, and we want to get rid of it. So we bring in alkene and it attacks the weakly bonded alcohol. So when we get this, it's kind of like double doors opening. So from the alkene, some electrons are going to attack the oxygen. That's going to be like one door unfolding, and then these electrons are going to like attack back. So that's another door. So that's how we get those 2 triangle things. I don't know if that made any sense. It probably didn't, but just turn the arrows into bonds again, and then you can see we get this epoxide, a nice triangle. And the rest of this just leaves. Yeah, it's like the electrons move around throughout the molecule, and it's like weird, but yeah, it just leaves.
Okay, so what exactly grabs the hydrogen off the end? Because I thought I guess the carboxylic O that's in an ether, I thought that's what grabs it. And then,
So basically, like you see this carbon has a double bond right now. When we kick off this whole thing, that's gonna flip. So now this oxygen is gonna get the double bond and this one's gonna turn into the alcohol. So when we attack this oxygen, these electrons make a double bond here. Since we can't have a 2 full octet on this one, these electrons are gonna leave here, and then that's what's gonna make the bond with the hydrogen.
okay. Thank you.
And the products are an epoxide and a benzoic acid. And then if you're starting with like a non-cyclic alkene, you have to look at the conformation of the double bond. So if it's Z, then in the epoxide, the 2 substituents are going to be cis to each other because they were cis to each other when it was an alkene. If we take a trans or E alkene, then the substituents after you do the epoxidation are going to be trans to each other like this. And I think that's it. Yeah, I think that's it for the reactions. We have a few minutes. We can do like a problem from the extra credit if you guys want.
Where will we'll be able to find this in the files?
Yeah, I'll upload it into files. Although I can't like upload it as a separate worksheet, so you're gonna have to dig through the chapter 11 answer sheet. Because I can't really upload anything without approval, so this is how I save stuff in for Canvas.
Okay.
Yeah.
So it'll be in the answer.
Yeah, so look in the answer sheet, and this is gonna be like sandwiched in the middle of it.
Did you do it like? For tonight, I thought you did the graded assignment, I plan on like doing that.
Yes.
I mean, I'll
Uh-huh.
try. I have a tight schedule, so I'll try to get it
If you
done.
can, yeah, thank you.
So my question is, so for the intramolecular WES, it can also turn into an epoxide or whatever. So how would you know, like, let's say he gets one of those problems and it says choose, would it be both? Like, you can either be the intermolecular WES and it could be whatever the last one you just said.
Well, okay,
You see what I'm
if
saying?
you have an intramolecular WES, that gives you an epoxide, it's not technically an epoxidation, it's still a Williamson ether synthesis.
Okay,
So yeah, just don't call it an epoxidation.
okay.
Like, it gives you an epoxide, but that's not the actual reaction.
But then this would give you an epoxide, so how would you know? by
Oh, the
looking at
reagents.
epoxide?
So if,
So one will have C, B, and.
yeah, the MCPBA
Okay.
or the CO3H, that's gonna be an epoxidation.
The problem that we saw last week, it made it easier. Like it made a four-member ring instead of a triangle.
Yeah.
So that would make it easier.